So, am I audible and is the presentation visible?
Yes, ma'am.
Okay. So, I remember last time we discussed the concepts, we brushed over the concepts of lateral earth pressure, and this week we were to do some questions based on it. So, we can start with that. Yeah. So, we have to determine the magnitude of resultant at rest in terms of force per unit length on the wall. At rest means that we have to use the K naught parameter because there is no active or passive pressure. At rest is K naught, and K naught is usually given by K naught equals 1 minus sine phi. At rest, force per unit length, mm, it's written like this because in geotechnical engineering usually we deal with plane strain problems. That is, let uh, let the problem, mm, see, the wall will be long in this direction, it will extend like this. What we do is we take a section of this problem, and we uh, basically plane strain condition. I want have I discussed plane strain and plane stress before this? uh, Rehan, have I discussed plane strain or plane stress condition before this?
No, ma'am.
Okay, so this is a good thing to know, so I will elaborate a bit. Basically, you know, when we are okay, so when we are solving for a problem, we say that this is a soil specimen, but actually, the soil is not two-dimensional. No problem is except for thin sheets or problems are usually, especially in continuum mechanics, we have three-dimensional problems. Then how can we uh, use only two dimensions x and y to solve our problem? It comes down to how we are framing the problem. So you can have some kind of symmetry. Based on this, we have plane strain, plane stress, axisymmetric, and your normal 3D problem. So What, uh, actually, let me write this way. Your actual problem is three dimension. And what you do is you idealize it. So it can be plane strain condition, it can be plane stress condition, or it can be axisymmetric condition. So here you have a sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. But you reduce this, for example, in case of plane strain condition, we assume that out of plane strain equals 0. Here we assume out of plane stress equals 0. And here we assume, I will mention, I will show it in a diagram. So out of plane strain in conditions, for example, if you have a long embankment, so the strain is delta, your strain is delta z length of z over length of z, isn't it? If this is in a very, if it is, let us say 100-meter even, we have 100-meter long embankment. So the strain in this direction will be, uh, let us, strain is usually maximum, let us say 1 mm, 2 mm, 5 mm, even 5 mm. So the strain in the z direction will be 5 over 100, 1, 2, 3. So this will be 5 into 10 to the power minus 5. But when you compare it to x and y sides, you may see, uh, first of all, the strain due to the fact that the length is long in this direction, and the fact that, uh, plus the fact that there is a confinement also take, which is, if I take a section here, there is a confinement in this direction that will prevent shears, strains to develop. So we assume that we also have Ez, Ex, Ey, Ez, gamma xy, gamma yz, gamma zx. Okay, so these are the unknowns in a 3D problem, the stresses and the strains. So what we do is we assume that in plane strain condition, that in plane strain is, 1 second, out of plane strain is 0. Okay, so out of plane strain is 0, we assume. So they, because they are related through your stiffness matrix, these two just go away, and these two go away, anything with z goes away. So you only have now sigma x, sigma y, strain in x, strain in y, and strain in xy, also sigma xy, tau xy. So this reduces the number of unknowns. And now if you are working in principal stress states, then you only have sigma 1, sigma 2, let's call this sigma 3, sigma 1, sigma 3, epsilon 1 and epsilon 3. These will be the only unknowns. So we reduce the dimension. In plane stress case, usually more appropriate for structural mechanics problems. If we assume that the material is very thin, like a sheet of paper, something like this. So the area here is very, like, the sigma x will be force in x direction divided by the length here. The sigma y will correspond to this length, isn't it? But if you see here, the force here will be concentrate. There is no area for this force. You understand what I'm saying? Usually, we have a when we say that we have a force, it's not actually a point force. It's over the whole length, isn't it? In y direction, but in z direction, you see, there will be a very small this thing. So we assume that the force, the stress in the out of plane, uh, the stress in the out of plane direction is 0, and then we get rid of uh, similarly sigma here, sigma here, and here. Okay. Then axisymmetric condition, what we assume is usually like your triaxial test. We assume it's not an assumption. It's not an assumption per se. It's actuality that in axisymmetric case, when you calculate your principal stresses, sigma 2 is equal to sigma 3. Sigma 2 is equal to sigma 3. So I'll not go into the derivation, but what we are left with is two stresses, and sigma, we take it as sigma theta, sigma r theta, and basically the stress in this direction, the stress in this direction, and what we want to know is the hoop stress, which is called the sigma rz. Uh, Sigma r, sigma z, sigma rz, which is the hoop stress, and the epsilon z, epsilon theta. Okay, so basically I mentioned this because of defining this condition, that we in plane strain condition, which we use in soil mechanics, we assume we uh, like here, this wall, we are solving in 2 dimensions. Actually, it's extending in this direction. That is why it is written force per unit length of the wall. That is, we are only taking unit length in this direction. And if you have to calculate the entire force on the wall, you will have to multiply it by the length of the wall. Okay. We can move on. Determine the magnitude of resultant at rest force. So the first thing will be we will calculate the vertical stresses. Let's do that. Gamma has been given. Remember that in lateral forces, always use effective stress, include water, pore water pressure separately. Because what we do is we say that Kh is equivalent to sigma h is equivalent to K times sigma V. This has to be the effective stress. You are not to use this multiplication of K on the pore water pressure, and that is why sigma h total will be K sigma V dash plus U. So here we have a gamma of 18 kilonewton per meter. OCR has been given, phi has been given. OCR has been basically given because one of the equations for K naught is we usually use 1 minus sine phi. The other one is there are actually many, but since they have given the OCR, I will write K naught equals 1 minus sine phi. I think it was into OCR. Just let me check. Yeah, OCR raised to power sine phi. So we can basically what we mean is K naught for OC soil equals root of OCR K naught for uh, NC soil. This is one way. And another equation has been given by Main and Kulave as this is Main and Kulave. Let's do one thing. Let us calculate using all three of these equations. K naught value we will calculate and then let us see how much difference in the results we can see. This will be 1, 2, and 3. This will be 1 minus sine phi, 1 minus sine phi raised to power OCR times sine phi. This will be 1 minus sine phi into root CR. Okay, let me open an Excel sheet.
Madam,
Yes.
what is the source for these three formulas, madam?
Uh, I think this is called the Jackie's formula. This is the, I will give you the actual sources. Just this is called the mean and Lave. Jackie's formula is yeah 1 minus sine phi. Then usually we use 1 minus sine phi. It's pretty easy. Consolidation সরি গেলে K naught NC is different given by mean. It's for clay it's different. For clay it is 1 minus 0.987 sine phi. For sand it is 1 minus 0.98 sine phi. Usually we don't use it. And then we have another which is there is this one Meyerhof has given in 1976 K naught OC equals K naught NC into UCR raised to power 1. So Meyerhof has not given an NC, So if you use Jackie's equation for NC, then it will become 1 minus sine phi into OCR root of this. So this is what these three conditions we will check. Okay. There are some more. I'll do one thing. I'll paste it here. Is that okay? Is that okay?
Yes, madam. Yes, madam. Thank you, madam.
So let me open the Excel sheet. So our question asks us, so phi has been given, which is 30. Okay. And we said that we will use three equations. Jackie's equation, uh, Kullhabe equation, Meyerhof. So this was 1 minus, uh, actually, in Excel, you usually have to give everything in, you have to give the angle in radians. So what we will do is this, we will use this function, which will convert our phi to radians, and then we take the sign for that. Okay. And let me use this, simplify. Kulave was 1 minus sine phi into, let's say, OCR. OCR, actually, it is better if I, yeah. And then we have OCR, which is 2. And we'll write this as 1 minus sine phi. This will be 1 minus Sin phi into OCR raised to power sin phi. And this will be 1 minus sin phi into square root of OCR. Is that fine? Basically, we should not be using Jackie's formula because this is for NC. Let us use Jackie's formula to calculate Meyerhof formula. Meyerhof formula says that K naught OC is equal to K naught NC into square root of OCR. So we will replace this by our Jackie's formula. Okay. So these are the two K naught values we will be taking. And let us divide our uh, height from this is the whole height is 6 meters, you know. Then Z we will take from top at 0, at 4, then at 8, 4, 5, 6, 0, 6. Height of the layer is okay. Then we have the gamma bulk, which is for this 18, for this it's 19 gamma sachet. Okay, so ग्राउंड वाटर टेबल नहीं है यहाँ एंड यहाँ पे we will have 10 kilonewton per meter for presence of groundwater table. So this will be gamma for calculating the effective stress. Gamma will be here this minus O water pressure, this minus pressure. Okay, let's call this gamma effect. And then C is 0. H times gamma W. So we will have, I'm writing it like this because when we move further, we will have to, if we have too many layers, or if we have to work on a cantilever, uh, if you have to work on a cantilever and a retaining wall, then there is a lot of bookkeeping, and it's good to store the data like this. Okay, so Okay, so we will have a distribution like this. This does not have any water table, so this will be just gamma times H, which is 4. And then we have a distribution like this, because we have to take the effective water content, effective stress, which will be gamma submerged times 2. And the total here will be 2 times gamma plus gamma submerged into 2. So this dimension will be thickness of layer multiplied by its effective weight. And then this here will be this plus thickness of layer multiplied by its effect. Okay, and in the water, stress due to water will be thickness of layer multiplied by your ground. Okay, this is effective vertical stress. Now we want to calculate the horizontal stress. We will calculate effective horizontal stress. Let's come back to this later. So using K naught 1 and K naught, this will be the later load will be here, and the later load here will be this multiplied by this. Actually, I should not add it here. We will add it later. We will just take layer wise first. Okay, I have to take this section. This is K1 times um, H gamma 1 H1. This will be K2 times gamma 2 H2. Okay, so K naught clay has been given as that if I use phi equals 0, I will have a K naught of phi will be 0. K will be 1 if I take phi equals 0. 1 minus sine phi OCR to the power 1 minus sine phi for 0 1 1. K naught is 1. Let me check where I'm getting this K naught from. K naught from clay. So let's use this formula. Basically, these are all empirical formulas now. We have K naught equals 0.19 plus 0.233 log of plasticity index is given by Kinney 1959. Okay, 0.1 0.19 plus 0.233 into log liquid limit, plastic limit has been given. Let's write it here. Liquid limit is 36, plastic limit is 14. So your K naught clay is 0.19 plus 0.233 into log liquid limit minus plastic limit around 0.5. We have for clay. Okay, this will be gamma effective. So this K into effective stress, take this as K naught into the effective stress here. We got to know the distribution here. we'll have 46.76 here, 9.05, and then we also have a water pressure here. This will be gamma W into 2, which will be 20. Okay. Total stress, total effective, total effective, and total stress will be the area of this. So we will have half of 46.76 into 4 will be the
Madam,
area here. Yes, please.
can I have a small doubt, madam?
Yes, 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 please.
Is it a layered soil? Yes or no? Sand and clay.
Yeah,
In sand and clay, when you have a layered soil, at the junction you should have a two different Ka, therefore two different answers you have to get now, madam.
what we have?
Two different phi values. Upper layer phi is 34,
Yeah,
lower layer phi is 0.
yeah,
Therefore, you are going to get the two different values of the earth pressure. You are using only
yeah.
46.76.
No, I'm not using 46.76 only. Okay, okay, okay. You're saying here.
Yes, madam.
Okay, 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 okay. Yes, that
Is it
is
correct,
correct.
madam?
Yeah, yeah, that is correct. That is correct.
Thank you, madam.
Yes, that is actually correct. Here you will have, I forgot about it. Let's see. What we will do is at 0, at 4, and then again at 4, we will have 19, 10, this, then we will have effective.
19, no, madam. Why, madam, 19? It is 18 only. Upper layer, but oh, gamma. Overburden is same, na?
Yeah, overburden is same, but
Therefore, why you have used gamma 19?
yes,
Right, madam. Now
just,
it's clear.
just okay, one. Basically, what we have to do here is we have to multiply the overburden with the clay cane,
Yes,
isn't
madam.
it?
Yes, madam. Yes, madam. Now it's clear.
Yeah, so we need to do this. What we need is we multiply with the overburden
Yeah,
with
same overburden.
clay cane.
Hmm.
Okay,
Thank you.
so yes, so we will have 46.76 here, and then we will go a little back at 36. 36.20 here plus 9.05. So at the base we will have 45 point something like this. And we have to calculate the area here and the area here. get the total stress. This the next page. The this is one this has been given in the question that I am discussing. This is perfectly all right because this is one of the formula that has been proposed for it. But we can also use, which has been given in the question, 0.922. Okay. Why I am using 2 is because here the value is high. So we will get a different kind of diagram than this. Let's use 0.922. Okay. So by using 0.922, we get 40. Let's for now take one equation only. This will be 46.76. And then we have another. Okay. And this here is 16.59. So what we will do is we have to calculate the resultant also at 1/3 height of this triangle, at the center of this rectangle, and at 1/3 height of this triangle. We have to calculate the moment about, let us say, a date. The total force is sum of all these forces, and total force into your lever arm will be equal into sum of individual force multiplied by their center. So this will be, let's say this is area 1, area 2, and area 3.
Madam, water table diagram you have not drawn, huh?
Right now, not.
Okay, okay.
Okay. So we will have an area here which will be 0.5 into your base into your height, and then you have an area 2 which will be simply your base here into 2, and then we have this area 3 here which will be 0.5 into your base into height, and the this is area 1, this is area 2, this is area 3, and lever arm or your X bar will be from the datum is at bottom. From the datum, this has an X bar of 1 by 3. From the datum, this has an X bar of 1. And from the datum, this has an X bar of 2 plus 4 by 3. Is that fine?
Yes, ma'am.
Is it? Mm. So for effective stress, we will have the
Madam,
total
liver
stress.
arm third one, check it, madam, once again.
This one,
Bottom one, madam.
bottom one will be 2 by 3.
Yeah, but you
That
have written H by 3. Right.
so then we have the total of force will be just sum of this, and then this will be area into lever arm from datum, this into this. Hmm. And we will get our lever arm as we will get our resultant, the position of resultant as um, this FIVI over FI here. So resultant position will be this divided by this. So for effective stress at 1.8, somewhere here, you will have a resultant force acting, the force will be equal to 242 kPa. If you talk about total, then we will have another area. This A4. Sure. We have 10 into 2 is 20 here. Area will be again half of base base into altitude. Hmm. The x bar will be again same 2 by 3. Ax will be this into this, and then we take the sum. Actually, let's the resultant for the total stress will be at almost 1.78. That is quite intuitive because we see that we have added the CG was here and we added a weight at the bottom, which is the weight of the water, and the CG just the resultant just shifted towards the heavier uh, area. Okay, so that was this question, and what else were we going to do with this question was we were going to check what was the difference between if we used Meyerhoff's formula or Colavir's. So we will take effective horizontal to be this into Meyer. This equals this will be same. This will be this into Meyer. Okay. And then this will be same and have same all of it. This is half of base into altitude. This is it actually has to be 2. This is area 2, and then area 3 is half of base into altitude, and then area 4 is for uh, triangle 2. It has to be half of base into altitude. Okay. And then we have this. Okay. So you see here, there is very small difference between the two results. The results with Kulave gave us 1.87 and 1.78, while with Meyerhoff's formula, it gave us 1.88 and 1.78, almost correct to the second decimal. But that is also because um, the OCR will always range between 2, 3. It will not go much over that. If it does, then uh, when your OCR is 2, uh, then this Meyerhof becomes this is raised to power 0.5, while Kullaway is raised to OCR raised to power sine phi. So here in this case, it was sine phi was already around 0.5, but your if we change 25 here, 25 here becomes 15. Okay, so now it's 0.25 here, and we will see a greater difference. Okay, because this is OCR raised to power sine phi, and that is raised to power 0.5. In our case, OCR was already sine phi was already nearing 0.5. That is why we got such close results. Okay, we can start with the next question. Was this clear, this difference in the results?
Yes, madam.
Okay.
Madam, can I ask one more question, madam?
Yes,
Why in Indian textbooks K-naught condition is not discussed for clay soils, madam?
K-naught conditions is very important for clay soils.
But Indian textbooks they will go for only active and passive cases when they Bell's using a Bell's equation.
Actually, if you think about it, in
And
K-naught condition,
even in our example,
yeah,
clay for clay they have not given any quotient value. If you go through the example, previous example, figure.
actually for clays, K-naught is dependent on your consolidation behavior. Okay, so basically, um, what we have during consolidation, what is going on, that itself is called the K-naught condition. Okay,
Yes, ma'am.
so you will have one second. Let me gather this. K-naught condition, basically, what you mean by K-naught condition is zero lateral strain.
Yes, madam.
And if you see your, there are two tests that we do. There is your triaxial test and your odometer test. So in triaxial test, you have a water-filled tank here, isn't it?
Yes,
So the lateral movement is allowed. The lateral strain is not zero, isn't it?
yes, madam.
So this is allowed such that, or the pressure is imposed such that uh, the pressure in all directions is equal. So we have an isotropic consolidation. But in oedometer, you have a ring. Okay. So ring prevents any strains, any movements in the lateral direction. One second. Just a moment. Okay. So the consolidation ring, it prevents any strain from occurring at the ends, and this practically is what K-naught condition means. So in this situation, when you calculate the sigma 1 and sigma 3, the ratio will give you the K-naught, isn't it?
Yes, madam.
So your question is, why isn't it talked about?
Indian textbooks, for example, Bell's equation is equal to active earth pressure is equivalent to
Uh,
Ka into sigma vertical pressure
uh,
minus 2c square root of Ka we use. That
uh,
means there is the effect of cohesion
uh,
for clay soil.
yeah,
But in our example, till now, what we have done, second layer clay, C is not given in the example itself. Why it is like? Look at here, madam. Clay, they have given gamma sat 19, LL
uh,
is given, PL is given, OCR is given.
uh,
Clay default phi is equal to 0.
uh,
But what happens to the clay cohesion? That is not given.
yeah,
That is my question. And cohesion effect also didn't come anywhere in our calculation. That is my question actually here. Upper layer is okay because completely sand, you don't have a cohesion.
I got.
Yeah,
But
that is.
but
Even in Indian textbook, K naught condition is not at all discussed in any textbook, Indian textbook, for particularly cohesive soil, sea soils.
see, you are saying that you
Yes,
use
exactly this one.
minus
What your
2c.
effect of that?
Uh, let me remind myself. What we
Yes.
used to study was, actually, I am a little bit out of touch with this
Yeah, you
subject.
can
So,
you can answer, madam, later. You can go spend some time and you can answer. This is I have raised a concern also in a problem solving session group forum. I have raised this question: why they don't discuss K naught condition in particularly
because
clays?
as I mentioned,
Mm.
like in you will basically, as what I understand from this is, usually you get what is it, Indian textbooks,
Mm.
instead of going concept wise, we go in a manner, the flow is in a manner that we can frame the questions around,
Okay,
isn't
okay.
it?
Yes, ma'am.
So, K naught is more, as I mentioned, it is more relevant in
Mm,
consolidation, even though it is not mentioned in consolidation also in Indian textbooks, as you said,
mm.
but it is more relevant
In
for
consolidation.
consolidation. It is
Mm.
also relevant, more relevant in your share failure or
Okay.
share stress strength topic,
Mm,
because there also, if you are assuming a K naught condition, that is, there is no lateral strain condition, then your sigma 1 over sigma 3, whatever you are calculating, that basically is K naught itself,
mm.
isn't it?
Yes, ma'am. Yes, ma'am. Understood.
Okay. So explicitly they are not mentioning, because
Mm,
till now, whatever we have been doing, that is for K naught condition only, because we were not uh, mentioning any kind of strain in the lateral direction. In the
mm,
passive and active earth pressure topic, that was the first time we talked about strain in the lateral direction. We have been focusing on stress in the normal direction, isn't it? And
yes,
now,
correct.
first time we are talking about strain in the lateral direction, which is in active or passive state. And for K naught, there is again no stress here. So that is why you will not see explicitly this being talked about, you see.
Yes, ma'am.
Okay.
Okay, okay, ma'am.
Okay. So next question. Determine Rankine active and passive forces per unit length of the wall and the location of the resultants. Let's do that. Since C is 0, your K active will simply be 1 minus sine phi over 1 plus sine. Okay. So your Ka will be, we can also calculate the Kp, because we have to calculate the active and passive forces. Kp will be simply the reciprocal of Ka. Okay. So determine the active and passive forces per unit length of the wall, location of the resultants. Active force will simply be Ka times gamma h. Passive force will be Kp times h. Gamma has been given as 16. H has been given as 6. P active will be first sigma H. Ka into into H. Sigma passive will be Kp into gamma into H. And the total stress will be sigma height. And the resultant at H by 3. So yeah, you see there is a lot of distance between the active and the is almost 14 means 15 times greater. Now this was a simple question. Just to show the result question. What we need to calculate is
Madam, can you increase the size of the picture? Yeah, madam. Yeah.
Rankine's active and passive pressure. Sand pi is different. What we will do is
Madam, before starting, can
yes,
I raise a small question?
yes, please.
When you're solving this example, what is our assumption in the wall? Do we have a weep hole or no weep hole? Because water pressure, sometimes weep holes are there, there is no pressure of water.
Yes,
If the
but
weep holes are not there, then pressure will be there.
yeah,
If
but
what is our assumption?
if there are weep holes, then there will also not be any stagnation of water like this, isn't it?
Uh,
Because there is a
uh
head here.
Okay.
If this was submerged such
Hmm.
that here also we had a solid body, soil body, and we
Hmm.
had a groundwater table going like this, then we
Hmm.
would have had okay, this is okay, that the balanced process. But because the water table is running from here, but here there is no, this is not a, see, if we had,
Understood, understood, madam. What you are telling, I understood. But
yeah,
do you have any retaining wall without weep holes? Sheet piles, there is no weep holes. But retaining wall, every retaining wall will have a weep holes.
yes, yeah, that is true. But what I think is happening here is uh, sometimes if you have, let's say, 3 meter from the ground is your first weep hole,
Okay.
then you have another weep hole. Usually the walls are much, much taller than this. You will have
Hmm.
weep holes at this level. Below this, there will be not any weep hole. So this will be this the pressure here, isn't it?
Yes, madam. Therefore, you are designing for higher pressure always.
Yes, and
Okay.
this 3 meter is very small if you think of
Okay.
um, 1, 2, 3. Yeah, I think if, for example, just an example, if you have first people here,
Mm.
then you may get this kind of situation.
Okay. Right, madam. Proceed. Madam.
Okay, so we have a Z, let's say H. This is layer 1, interface 1, layer 2, and we have a height of 3. Then we have a gamma 16, 8. Have gamma sigma B will be H. This again will be in H. This will be H. Then we have value of Ka and Kp.
Madam, at L2, sigma effective should be cumulative. Now, why you got 24?
Because I am taking like we did here now.
Independently, you are taking.
Yeah, we did the
Yeah, junction
breakdown.
layered soils.
हाँ, layer
Okay.
wise कहाँ गया वो?
Yeah, yeah, I understood, madam. I understood.
Okay,
Right.
so you will have a Kp of Then you have a six horizontal. KA.
Ma'am, sorry, madam, sorry to
Yes, yes.
interrupt.
No, no issue, no issue. You can always ask me a question.
The K, KP values are answers are wrong, madam. For 30 degrees, it's a 0.33, no? Some error is there. Check it, madam. First layer 30 degrees 5.
Okay, I did not divide
You have taken
by 1
equation of
plus 5.
rest condition.
Yeah, yeah.
Uh, Copy it
Plus,
and change the sign, madam. Everything.
huh?
Same thing, numerator you can copy and change the sign.
It's okay.
KP is inverse.
Okay.
Yeah.
KA times sigma V. Okay. Also have a U here. Then let's draw this. — 16. Then we do 77. 88.5. We can again have, this is the effective. Then we have the we can calculate the resultant and the just a minute. So we will have an area 1, 2, 3, and this area 2 will be simply base into this way 0.3 this order then we this will be the same here also. Again 1, this will be same. And then we calculate the total. Here. Shortcut to this. Explore. Passive. Explore. This. So we will have a resultant about 3 meter for active pressure. So pressure it will be a bit higher. What you can think about is that active pressure has a shorter base, passive pressure has a larger base. So based on the mass distribution of the triangles, active pressure will have a short, uh, uh, lower this active than passive pressure, isn't it?
Yes, ma'am.
Okay, I think that is it for today. Any
Thank you,
question?
madam. No, madam. Thank you, madam. When you are going to cover about back pressure?
Hopefully in next.
Okay, madam. Thank you.
Just a moment. I think we have some time, and let me check if I have that with me right now.
Yeah,
I
as you like, madam. No problem.
no no because we do have some time, we can cover it today. No, I had downloaded something.
If there is any literature, also pass it, madam, for self study.
So that But unfortunately, I'm not able to find it right now. It's better that we,
You can cover in next class also, no
yeah,
problem.
we can
Yeah,
explore.
thank you, madam. Good night. Yeah,
Good night.
good night.